is going to be a bit of a rambly kind of talk, where I'm going to tell you a little bit about the kind of work we've been doing for many years now, but more recently applied to post-quantum crypto, and try to give you a sense of what this thing called formal methods or formal verification can do, what it can't do, where we are right now, and where I think this field is going. So what is formal methods? What is high assurance crypto in the sense that I use it? It's also called computer-aided cryptography. Typically, what we mean is, can you do proofs, formal proofs, mathematical proofs about your cryptographic system in a way that can be checked by a machine? So machine checked is kind of an important aspect of this. And what that means is that if you're designing a new crypto protocol, you might want to analyze this before, while you're designing it. Once it's become a specification or a standard, you might definitely want to fully analyze it comprehensively before it's published. And then you might even want to verify implementations of it. So all of this together comes together in this field. And there are different people who work on different aspects of this. But an important thing that I would like to emphasize is that the story is not done when you do your first proof. It's not something you can just put aside, because systems keep evolving. Even OpenSSL, as we know, for 25 years keeps evolving. And so does TLS, so do crypto algorithms, and so on. And so whatever methodology you want to do here, you want to keep being able to repeat it. And that's where the machine-checked value comes in. Because a pen and paper proof, updating it is kind of painful. But a machine-checked proof, you can keep updating it. You can put it on your CI. Just to give you a sense of what kinds of things I'm talking about, let me start with something which should be very familiar to all of us, which is TLS 1.3. And if some of you followed the standardization of TLS 1.3, you would remember that there was a whole bunch of drafts. But there was something weird that happened with that standardization, which is that as the standard was evolving, there was a bunch of researchers who were working in parallel to try to analyze it. The formatting has gotten a bit screwed up, but there were the drafts in red were drafts where the researchers found attacks during their analysis, and it was fixed in the next draft. The things on the right are all papers that were published while the standardization was happening, and this was very unique for academics. We hardly ever used to analyze a real-world protocol before it's being standardized, because, what's the impact factor? But there was a nice back and forth between the standardization and research there. And the bits in green, the papers in green, are the ones for which there were machine-checked proofs. So that is what I'm kind of focusing on here. So what were the lessons that we learned from this, and what is the impact of this, right? So the first thing is that this close collaboration between the protocol designers and the researchers was very valuable, actually, because in some cases, there were some design constraints from the protocol side, which the researchers would never have gotten if they didn't actually talk to the designers why they were doing some things in certain ways. And in papers, we would normally have just thrown those details away, but we actually dealt with it because the protocol designers told us this is important. Conversely, the researchers would say, well, this kind of construction is going to be very difficult to prove correct. If you don't separate these keys out, the proofs are going to be much more complicated. And the designers are willing to take that on board and say, OK, we'll just add an HKDF with a different tag, and that'll separate these two keys, makes the proofs easier, even if there is no explicit attack. So there was a back and forth, which was very valuable. And at the end of it, there were many proofs, some pen and paper, some machine-checked proofs, some attacks were found. And the process was considered valuable enough and useful enough that it has kind of become a de facto standard in the sense of how we want to design protocols now. So in the IETF itself, you'll see many working groups have started adopting this methodology of doing formal proofs before the standard is published. And even outside the IETF, you'll notice that Apple's PQ3 signals, PQXTH, the PQ Connect protocol that Tanya presented yesterday, all of these now have formal proofs, formal analysis of the protocol already before the first publication, before the first release. So it's become kind of a standard thing to do because of this. And a lot of the new things that we're doing all have machine-checked proofs, because that's something that people are getting behind. Just to give you a sense of this, Stephen talked about the ECH protocol earlier today. So since there was already a formal model of TLS from the TLS 1.3 standardization setup, we were able to take that model, extend it with ECH, and do an analysis of the new protocol. So as ECH was being standardized, it's not 25 drafts, but many drafts before, there were quite a few kind of attacks, let's say, against the protocol or against what people expected that the protocol should do. And this kind of analysis was able to kind of find those attacks, but also prove that the final version does not have those classes of attacks. So it's very valuable to be able to quickly take a massive model like TLS 1.3 add a feature, and analyze it for these new properties that you want from this extension. But all of that is for the protocol, the standard, okay? But here we are in the OpenSSL conference, we care about implementations. So what kind of guarantees can we give about an implementation of TLS, right? So the good news is that there are many components that you think of as core components of protocols for which there are nice verified components that are available today, formally verified ones. For example, there are many crypto libraries. Dan talked about some of them yesterday. I'll talk about some more. There's also verified parsers for all the TLS formats. There is a verified parser now for X509. These are written in C. There are zero-copy parsers. And they're formally verified, so there's no memory out of bounds, but they're also provably correct. And those things are very cool. I think it's worth looking at. There's also verified implementations of the record layers, high-speed kind of implementations, which have been proved to be formally correct. So these are all components that have been proved. There's no one holistic thing that is in one system that you can point to and say, oh, there's a verified implementation, until the next slide at least. And it's one of those places where you might ask, well, OK, all these components are there, but what about OpenSSL? Can we actually verify the protocol layer in OpenSSL? I'd say today the answer is no, because the tools that we have available can do these well-defined components quite well, but the effort to scale up to all of OpenSSL is too much. Because each of those components, the results that we have, took several PhD years to achieve. Now that we have learned from them, and now it won't take many PhD years, but it's still too difficult to apply to legacy, handwritten C code, which was not written to be provably easy to prove. And one of the key things there is that when we do these kinds of proofs for C and for assembly, whether it's for crypto, for parsing, for whatever, about 90% of the time we spend is on proving memory safety. Just proving that things are in bounds is like, by far, it's a very boring task. It kind of kills PhD students. But that is, unless you do that, you cannot prove anything else. And you spend most of your time actually doing that sort of thing. So what ends up happening is that most of the successful projects which have landmark results, what they do is they don't actually verify like the C code from OpenSSL or the assembly code from OpenSSL. There are a couple of projects which do that, but mostly we don't. Instead, what they do is they define a domain-specific language for which proofs are easy to do, and from which they generate C or assembly. And doing that, you can do a lot more, a lot faster, and you don't basically destroy PhD students. So the question then becomes, well, what about a full TLS implementation? Can we actually prove something about a practical TLS implementation? And the answer is yes, and I'll get to that. If you want to see some of these lessons learned here, there's a nice paper that we just published on the project Everest, which was like a 5-6-year project trying to verify a TLS stack. And there's lots of positive and negative lessons from there. So what will be the final slide of this talk will be about this implementation that we are building called Bertie, which is the verified TLS 1.3 implementation in Rust. Not in C, but in Rust. And that, we believe, is doable. We're doing it for Bertie, but I think that's doable for other Rust implementations at a level which is much higher than you can actually do for C today. Okay? But let's put that to one side and then build up to it. The first thing you need for a verified protocol implementation is a verified crypto library, because that's like the core bit in there. And the good news is there's many, many, many cryptographic libraries which are formally verified today. So Dan Bernstein talked about this already. I think Doug Stabila, if you saw his talk, lots of people are talking about formally verified crypto. And there's a whole range of them. In fact, they keep increasing. The last time I wrote the slide, Microsoft hadn't announced its formal verification project either, but Microsoft has one, Amazon has one, rumors are Apple has one, other people have, everybody is trying to formally verify their crypto. And using a variety of techniques. You don't need to know what techniques they are, but there are a wide variety of techniques being used for it. So what does this mean to verify crypto, right? So what is this workflow? The basic idea is you start from the standard. The standard is something like this is the Cha-Cha Poly standard from the IETF, which has some pseudocode in it, some English language, some pseudocode, some test vectors. You take that and you convert that into a formal spec, okay? That's the formal spec of the Cha-Cha 20 round in a language called F star. This is the same formal spec in a different language called EasyCrypt. There's another one in Hall Light. There's another one in Coq, whatever. You can keep writing formal specs of that. And Charter20 is easy. It's a permutation. It's very easy to write. But you can also write X25519. You can write your lattice crypto in the similar style. Once you've written your formal spec, you take your code, which is down there, which is hopefully highly optimized, might be doing all kinds of optimizations, might be using AVX2 or AVX512, whatever, and you prove that it meets the formal spec. And what we mean by meets the formal spec is at least 3 kinds of properties you might want to check, depending on the language you're in. Is this memory safe? So is it ever going to access things out of bounds? Is it functionally correct? As in, does it have the same input-output behavior as your spec? And then you might want to ask, well, does it have side channels? Is it constant time? Does it suffer from certain kinds of fault attacks? There's a whole range of things that you can ask. And if you find those bugs, during a web verification, you fix and you re-verify. That's the basic idea. And you can do this with a wide variety of tools. I'm not even going to list them all. And the good news is for almost any modern crypto algorithm you're using, say in TLS 1.3, TLS 1.2, in WireGuard, in Signal, there is a formally verified open source implementation under a nice and liberal license that you can download and use today. You don't have to verify it. It already exists. And the performance of many of these things is pretty good because some of them are formally verified assembly. Like Dan was talking about S2 and BigNum. There's also libjade. There's also Veil. Pretty fast code, which is fully formally verified. And the proofs are mechanized, which means that you only need to inspect the theorem. And of course, you have to trust the prover, but you can run the proofs yourself. Okay? Mostly, you don't have to read the proofs. You only have to read the theorem. And this kind of thing is now being used in AWSLC, in boring SSL, in NSS, and a whole bunch of places. So let's see. So this is a project that I've been involved in called HACL Star and Evercrypt for many years. So this is just an example. One example of this. This is a library that contains all of those algorithms that you see. Okay, and now it's even more than that. This is the last time I actually made this slide. Some of this code is portable C. Some of this is assembly. Some of this uses SIMD. Some of this doesn't. So all kinds of things. So these are a whole bunch of implementations, all of which have been formally verified. Okay, and this is also deployed. It's in NSS. It's in WireGuard, and so on. But to get there, to get to this complete picture, it takes years and years of both researchers and PhD students. And it takes years and years after that to keep maintaining it, because proofs need to be maintained as the tools improve, as you do small optimizations, and so on. And so in this project, which is kind of typical of the area, the code was all written in this weird academic language called F star. And from F star, there are compilers that can take that to C, to assembly, to Rust even. And so that's the basic world in which we were in. But if you say, OK, I've got all this code already in OpenSSL, can you just take it and verify it? It's too hard. We can't do it. There are some bits of it that have been verified. In fact, Andy Polyakov and the CryptoLine people got together and verified some assembly routines for BigNum, arithmetic for elliptic curve stuff. But all the variants of all the protocol, all the algorithms in OpenSSL, impossible. Even if you said just the 7 variants of X25519, maybe if somebody threw enough money at it, but it's quite hard to do that for code that was never returned to be verified. If you wrote something with a proof-oriented way, which is what Amazon is doing, then yes, you can verify even the assembly quite well. So how do we get to post-quantum? So that's the next thing. So that was the legacy world. We saw some TLS. We saw some crypto. How do we get to post-quantum? The first thing is post-quantum crypto. So here's MLChem. So how do we write and verify an implementation of MLChem? Many people are doing this right now. We are doing this too. Our strategy is to write it in Rust and verify it from Rust, because we don't want to write it in the domain-specific language like F star. We want actual crypto developers to be able to write this code. But at the same time, we want to have a type-safe language, a memory-safe language, so that we don't spend 90% of our time just proving bounds. So we start from Rust, and we have a toolchain which will compile Rust to a variety of backend provers, including F star, Coq, Proverif, and so on. So using this, we use this particular pathway. So we write the Rust code, MLChem code in Rust, and we compile it using this toolchain called HACS to a model in F star. On the side, we take the FIPS 203 draft, and we also write a specification in F star. We also have some bunch of libraries which model various things about the Rust library, the Rust core, and so on. And we throw all of these into the prover to prove the properties that I spoke of. If the proof succeeds, there's also a compiler which will take the verified code and spit out C code. So normally, we shouldn't need this. We already have the Rust code, right? But there's a whole bunch of libraries, including NSS, including OpenSSH, including boring SSL, whatever, who can only consume C code today, so we do this. But we really believe that this part shouldn't be needed. Eventually, if people are able to consume things, they should consume the Rust code. And that's what Signal does. So Signal, the post-quantum Signal that has been released this last week, they use the Rust code from our MLChem. So what does the verification look like, just to give you a sense of it? So here's a Barrett reduction function, which is very simple for MLChem. This basically does a modulo arithmetic modulo 3329. It's not exactly the modulus. It's basically plus minus 3329. Okay? But this is the code that you will find in many MLChem implementations. Okay? Interestingly, of course, it's not going to do modulus because that would not be constant time. So it does some complicated arithmetic to get there. Okay. Even looking at that arithmetic, I can't tell whether that's actually doing the modulus with 3329, but it is. Okay. But this is a signed integer modulus. Okay. The first thing to notice is that there are operations here which can overflow, like Nikki was showing us about SHA-3 yesterday, but this is also an overflow, potential overflow. So this it's not the case that this function works for all inputs. But if you take any I32 and try to plug it in there, it's not going to be producing the modulus. In fact, in some cases, it's going to overflow. That's the first thing to notice. And even in Rust, which is a memory-safe language, there are arithmetic overflows. Okay? In debug mode, that will panic. In release mode, it'll just wrap around, but it'll give you the wrong answer. Okay? So the first thing to prove is that none of this code will ever overflow or underflow. And then, to do that, you basically have to say, OK, what is the range of the input? So we say the input is between this minus Barrett constant plus Barrett constant, and the actual value doesn't matter. And if that is the case, and I can guarantee to you that the result is between minus 3328 and plus 3328 inclusive. So this is bringing it to the right range. So a lot of the analysis here is really to show what is the range of inputs that I'm allowing, and what will be the range of the output. And if you give me inputs in that range, I can also prove that the result modulo 3329 is in fact the input modulo 3329. Okay? So that's a spec that I can put on this function. So that's my precondition, that's my postcondition, and this basically says what the guarantee is. So that's, adding that spec, running hacks, running f star, I can prove that the function there, automatically I can prove that using an SMT solver, but automatically that in fact it is a correct modulo function according to that spec. The next question is, what about secret independence? Because the whole point of this modulus function was to be constant time, not to leak. So at the Rust level, there's very limited stuff you can do, because we are at the source code level. The compiler will completely screw us over. But even so, at the Rust level, we can at least impose some source code coding disciplines that ensure that some egregious side channels are not being introduced. So for example, in this world, what we ensure is that the arithmetic operations, non-constant time arithmetic operations are not allowed over secrets. Secrets are not used to index into tables, for branching, and so on. So this is preventing a certain class of timing channels at the source level. But of course, the compiler might be introducing new channels. We have no idea, right? So that we cannot protect against. So what we do is we formally verify the correctness, the memory safety, the panic freedom, no overflows, no underflows, and some disciplines like this. And then we have to run tools on the generated assembly to make sure it didn't introduce some side channels. We hope that the compiler is not introducing incorrect memory accesses and incorrect functionality, because that would screw up a lot of stuff. But the side channels, we know it probably introduces in some cases. So just at the source level, we can find attacks like Kyber slash. So Kyber slash is just a fancy name for a timing channel, which was there in this particular piece of code. It was there in the Kyber reference implementation. which was submitted to NIST, and in several other implementations. It even made it into some early versions, some products. And that was basically because there was this division here, and on the left-hand side of the division, there could be potentially a secret. Okay. On certain platforms with certain compiler options, that could be a side channel. And this kind of thing we found while doing a verification of our Rust implementation. So in our Rust implementation, we were analyzing it. We said, oh, there seems to be a side channel here. It's not secret independent. And we fixed it. And then we went and said, well, let's look at other implementations. And then we went and looked at other implementations, and we found the same issue there. So what we have is this library called libcrux, which has a portable implementation of MLChem and MLDSA in Rust and in C, because the Rust is compiled to C. This code is now deployed in Firefox, OpenSSH, and Signal. Okay? And it's formally verified with the caveats that I said about the constant timeness. And that's the crypto library. Right? So let's think about what the... How much time do I have here? What about the protocol layer? So here, let's look at an example, which is Signal. Right? So this is a classical Signal protocol. It has something called X3DH to do the initial key exchange, and then it has this ratcheting protocol, right, that it does. So it does a double ratchet. And it gives you all kinds of lovely properties, including something called post-compromise security, and so on. And recently, or 2 years ago, Signal started that post-quantum transition by first changing X3DH into something called PQXDH, a post-quantum version of X3DH, where all they did was they added a new post-quantum chem thing to mix in with all the other keys they already had. So they already had 4 Diffie-Hellmans happening. They added a post-quantum thing, chem to it. So in that sense, it's a very simple change. They just added stuff on the side. Okay? And of course, since the post-quantum key is sort of like a long-term key, longish-term key, they were signing it. So they signed the post-quantum key, just like they sign what they call the signed pre-key. Okay? And this is something that they published in 2023 as a spec for PQXDH. So I and my students were very curious about this. We kind of plugged this into a formal verification tool, did an analysis, gave them feedback, and we found some issues. So a priori, PQXDH is very small addition. And there are many, many proofs already for X3DH. Okay? So that's like well-analyzed protocol. So small addition should be easy to verify. In fact, we ourselves had a proof of X3DH. So we just added PQXDH and said, hey, let's try to see if this is true. So there are 2 questions to always ask here. The first is PQXDH as secure as the previous protocol, even if you don't consider a quantum adversary? And this is a very important step. I mean, let's just keep considering the classical adversary. Are we making the protocol less secure? And then you can ask the question, oh, are we getting extra security against a store now, decrypt later, or harvest now, decrypt later adversary? So methodology basically was we took the protocol spec, we wrote a model for it, which includes the crypto assumptions, the protocol model, the security goals, the compromise model, what can be compromised when. And the first thing we did was we analyzed it using a tool called ProVerif. This has a symbolic protocol analysis. And this can very quickly find you attacks. So once you find an attack, you fix, and you recheck, and so on. And once ProVerif cannot find any more attacks in the symbolic model, then you might want to do a proper crypto proof. And for that, we use a different tool called Cryptoverif, which happens to use the same syntax. So you can write the same protocol, analyze it with ProVerif, and then analyze it with Cryptoverif. And to analyze the Cryptoverif, you really apply your assumptions, and you say, oh, can I prove it? If you can't, you might have to refine your assumption or fix your protocol, and you go back and forth until you have effectively a pen and paper proof, but a machine-checked proof that in this case. So we formally specified PQXDH. The details are not so important. These slides will be available online. You can stare at it later. But yeah, this is what a model of PQXDH looks like. This is half the model, so it's not very big, actually. And then if you run symbolic analysis ProVerif, it'll give you attacks. It'll say, here's an attack. And you'll say, maybe I was asking for too strong a property. Let me weaken it. Oh, here's an attack again. Here's an attack again, until finally it says, no, I can prove it secure if you limit your goal to this very specific goal. And the Cryptoverif proof kind of looks like this. It's a game-based proof. So it basically is like apply this game, then you do some transformations, then you apply another game, you apply some more transformations, apply another game. And if you apply all these games, finally you get to a protocol which is obviously secure, where in fact you can prove all your properties trivially. And then, of course, you have to do the quantum adversary, because that's the whole point of PQXDH. And you can define the passive quantum adversary in different ways in ProVerif and CryptoVerif. There are various, this is still a very active area of research. I would say that if you especially want to consider an active quantum adversary, almost no tool is able to do this right now. But for passive quantum adversaries, or store now, decrypt later, there are some very nice formalisms. So CryptoVerif, for example, has full support for it, as described in that paper. So we use that in this analysis. And while you're doing this analysis, you can find attacks. So the attack that we find on PQXDH, the very first version, was in fact there is a confusion attack where the post-quantum public key could be swapped in place of the signed public key and vice versa. You can switch the two. Now, in reality, it should not be possible, because this guy is about 1 kilobyte long, and that is 32 bytes long. But in the model, it's definitely possible. And you can imagine a situation in the future where this could actually be an attack. Or if the implementation is just looking at the first 32 bytes or whatever, this could be an attack. So it's not an attack as such, but in the model, this is a vulnerability. And that's because the signatures that we were using in the two were not tagged properly. So in fact, the two signatures could be swapped with each other. Signatures would succeed, and then you might discover, oh, the length is too large, so I'm going to reject it. But the signatures will succeed. And that's interesting, because here is a cross-protocol attack which can affect, in fact, the old version of Signal. Like X3DH can be broken because you introduced PQXDH, because this signature could now be used in X3DH. Okay? And that's kind of a class of attacks that we have to be very careful about when we do this post-quantum transition, which is, we have new protocols, we have old protocols, how do they interact? Are we actually breaking security when we were trying to improve it? So we fixed all these attacks. There was another one, a nice, interesting cryptographic attack called key re-encapsulation, one of the first ones in the wild of this notion of like chem binding that everybody's been excited about, that we found in PQXDH. And then we fixed those things in collaboration with the Signal team. They published a new spec. They fixed their implementation. And this is all good. And this whole process from the initial draft, our analysis, them fixing it, our proving a theorem about the fix, the whole thing took 1 month, and using machine check proofs. And that was 2 years ago. Today, we are much more advanced. We can take the full Signal protocol. Last week, they announced their ratcheting protocol called SPQR. And this time, we worked with them from the very beginning. From the very first version of SPQR, they were using ProVerif to analyze every single design. And they came through about a dozen designs before they reached the final version. And they analyzed each one of them in collaboration with us until they had a formally verified design, which they then implemented. And when they started implementing it, they were writing it in Rust, and they were verifying every single variant of it using hacks and F* to make sure that there are no panics in the code and to prove correctness for certain aspects of it. So this is an ongoing process, and it's in CI, all of these proofs. And this is very much part of the Signal repository now, and the way they're doing development for this post-quantum branch. So I promised you in the beginning of the talk, we'll come back to TLS, because they're OpenSSL. So what is this thing, BERT, that I'm talking about? Well, BERT is basically an implementation of TLS 1.3. And if you remember TLS 1.3, there is a lot of different aspects of it, right? There's the key schedule, there's a handshake, there's a record, and so on. And we verify it all. Okay? But we use different tools to different parts of it. In particular, we use 3 different tools. We use F* to do the formal verification that the code never panics, that the parsing is correct, the serialization is correct. So correctness properties. We use SSProof to do the cryptographic proofs of the key schedule. So this is actually crypto proofs. And we use ProVerif to analyze that the handshake code is actually implementing the handshake correctly, that is actually secure. So we prove protocol security here, cryptographic provable security here, and code correctness here. But all of this is driven off the same Rust implementation. All these proofs are happening for the Rust implementation, not for some abstract model. So just to give you a sense of it, we are really relying on a whole combination of things. The Rust type system is what we use for doing things like secret independence, like we already talked about, but also state machine invariants to make sure that the state machine has to follow a certain path. And for this, you can use the linearity in the Rust type system. We use verified cryptography from libcrux that we saw earlier. We use F* for parsing correctness and panic freedom, ProVerif for protocol security, and SS-proof for cryptographic proofs. And so the proofs of this, all of this stuff is about this much. So what is the total number of lines of code? There's about 3,000 lines of code in the implementation. So it's a very minimal implementation. Only does TLS 1.3, only does a couple of cipher suites, very, very small. So it's not a real implementation in that sense, but it runs in Rust, and it's not too shabby, not too slow. It also has post-quantum cipher suites built in. Then the handshake state machine and the core protocol code is about this much, and that's what we analyze in ProVerif. And within that protocol, this is the number of lines of code of the actual key schedule, which is doing all the key derivations, and that's what we analyze in SS-proof. Okay. This is a paper that is appearing next week at CCS, so it's online there, and you'll be able to find it and see what we actually proved. All right, so I'm going to basically stop more or less here with some lessons and open up for questions. And the first, so I showed you quite a few different things you can do with formal methods, with machine check proofs, and so on, and they are very different in spirit, and they fall at different parts of OpenSSL and the protocol landscape. The first is verified crypto. So fast verified crypto is already available now. So Amazon does this, Microsoft does this, Google does this, NSS does this. So maybe OpenSSL should also do this, right? But in that world, one thing that I say is still hard, very hard, is to take legacy C and assembly and verify it. That I think nobody has been able to do this at scale. It's just not possible, especially if you have a whole bunch of platforms like we do in OpenSSL. So Amazon really cares about Graviton 2, Graviton 3. They can throw money at it, and they can do proofs of their assembly code for those few platforms that they care about. And if there are few algorithms and a few platforms you care about and you have enough money, you should definitely do that. But if you take existing code from OpenSSL, it's going to be very hard. Rust, we believe, offers a nice sweet spot where you do have both high-speed, kind of fairly low-level code, C-like, but at the same time, it's actually verifiable, okay, much more than C is. The second lesson I would like to take away from here is that when you're transitioning from pre-quantum to post-quantum, it's not just about swapping the crypto. In fact, like we saw in the PQXDH example, there are many things that can go wrong, both quantum-specific, chem-specific, and also generic cross-protocol things that can go wrong. So you really do need formal analysis to do it, especially to kind of protect against downgrades and cross-protocol attacks. And the last thing is that verifying protocol code, I think, is the next barrier. I think verifying crypto is a solved problem from the research viewpoint. It's just a matter of propagating it and using it more. But verifying protocol code is still kind of a very open and very valuable place for both research and for implementations. We believe that this only works if developers and proof engineers can work hand in hand. If the researchers have to go and verify all the protocol code in the world, it's not going to happen. And to that end, again, we find that the new Rust-based verification frameworks, including ours, but many others, are very kind of being shown to be very effective at protocol code verification. All right, I'm going to stop there and open it up for questions.
Hello, I have a question that how to verify that your formal verification, that is the formal model, matches the original code. That is the correctness of the model. I know it could be easy in the verification of protocol, as they usually published in peer-reviewed papers. But to verify a code, which usually appears in open source libraries, how can developers check the correctness of the model?
It's a good question. Thank you. So suppose you take code that is in OpenSSL, right? So let's just take the handshake state machine in OpenSSL. It's very hard to isolate that piece out, but suppose you could isolate it out and have a piece of C code there. Then you can try to prove, there's a bunch of C verification tools, including a tool called CBMC, to prove that that actually is meeting some formal model that you've written on the side. Now, the formal model itself might be wrong. You have to be careful to be sure that the formal model is right. But hopefully, it's really small. And you can prove that this big piece of code really matches what this formal model says it should do. In our world, what we do is we do the same thing, but for Rust. So for Rust, there's a whole bunch of verification tools now. So you can take the Rust code, you can write pre and post conditions that say, OK, this function goes from this state to this state. This is what the input should be. This is what the output should be. And that's a full spec of what the handshake state machine is supposed to do. And you can prove it using or kind of either automated tools or proof assistance and a variety of tools that kind of can be used to do this.
Can check themselves without.
So that's what the Signal developers do. They themselves write pre and post conditions, and then they use formal verification tools to prove that their code is actually doing what they think it does. For the most part, this is basically to show that things are within certain ranges, things don't crash, there's no panic at runtime. Occasionally, they also prove some correctness properties about the way they use Galois fields and so on.
Thank you very much.
Next question at the very front.
And work, really enjoying it. I wonder, two questions. If anyone is checking that the models, different models you mentioned, libj, the HACL, EasyCrypt, maybe are interpreting the original spec in the same way. Second, you sort of already touched upon that, how to onboard more people and how would you start, maybe what's the success story with Signal, like how easy it was for them to actually start writing the formal verification stuff themselves and not really relying on researchers doing it maybe for them.
Yeah.
Thanks.
So one very interesting question is, how do you know that who watches the watchman, right? So how do you know that the model itself is correct and is consistent between the different tools? So it's hard because, of course, the model is a source of truth, and somebody has to audit this carefully. And often it's written in a very weird language like F-star or EasyCrypt or Coq, and it may not be easy for a standards person to actually go and read that and make sure it's correct. So what we do and what we advocate for this is, first of all, that your spec itself should be testable. So you should be able to run all the test vectors on it, maybe fuzz it against what you think it should be doing. So you should be able to run your model as if it were a reference implementation. That gives you some level of confidence you can compare and contrast against the others. The other thing, there's an idea called HACspec, which is a shared spec language from which you can compile down specs in all of these different languages. But again, it's like introducing spec language n+1 when you already have a problem of having n spec languages. So I don't know how much we can believe that. And there are some people, what they do is they kind of embed all of these spec language in a framework like Coq or Lean, and they try to prove that they are actually consistent. Now, again, that is a bit pedagogical. I'm not sure how valuable it is. I really believe in the testing idea that you should test your specs. And your specs should be really short and succinct and beautifully documented so people can read them. But because that is a kind of a soft answer. And the second question was onboarding more people. Yeah, so this is the big challenge. Right now, all the big proofs that you see, including the one that Amazon does, is really done by academics, even though they're hired by Amazon. They're really academics. There's like heroic efforts done by a few groups of people to do these big proofs. And I think that is not sustainable. For crypto like X25519, it is sustainable. You only need to verify it once. But for all the new stuff that's coming through, including post-quantum crypto, for the protocol layer, I think we need a lot of people like you guys to be able to use these tools. So there is a whole effort on, both in the IETF, this UFMRG, and this workshop called HACS that I help co-organize sometimes, to actually make the tools really much more usable. And one effort towards that is to try to use more and more tools like Lean, which it seems like are much more accessible to programmers to be able to do proofs than the previous tools that we have been using. So, but it's the ongoing work.
There's another question in the front. Please, sir, go ahead.
Thank you, Karthik, for a really interesting presentation. The conference is almost at the end. You're one of the last talks here. So as you've been attending sessions here and having discussions, I was wondering if there's perhaps some new insight that you got here at the OpenSSL workshop. Something that may come to mind, like a short answer, no, is of course possible, but perhaps there is something that you'd like to share here with the audience.
Well, one thing, of course, that one notices when you come to a conference like OpenSSL is how many concerns in programming, extending, and so on, OpenSSL, like the previous talk, are nothing to do with the crypto or the protocol. There are so many things other than the core crypto and the protocol that we academics tend to be obsessed by. that kind of form part of this gigantic library and the way it's used. And sometimes the way it's used is unusual enough that we are maybe optimizing the wrong things. So I think there's lots of learnings to be had from the community on what the research should be targeted towards. And we can spend all our time maybe verifying just X509, and that'll be like a 3-year project. But is that actually valuable or not? We could spend all our time verifying this small part of the world, but maybe you find that, in fact, that's not valuable. So there's kind of interesting insights there, but I haven't yet fully digested it.
There was another show of hands. Please go ahead.
Yeah, so following up on the previous question, what language do you think IRTF and IETF should adopt for, like, I think the specs should have actual code, not pseudocode.
Yeah.
Right, so what should they be using? F-star or Lean or Coke or whatever?
So we've been talking to people for a while now about this, and even in the IETF and the IRTF, there are different communities, right? So there is the cryptographers who seem to like Python, basically. I mean, in the end, we've gone through a whole range of languages in discussions with lots of cryptographers, but finally, Python or Sage-friendly Python, let's say, is the one that people writing crypto specs seem to like. But I don't think that is suitable for protocols, right? So for protocols, especially message formats, and then the state machines and so on, I think there is a different language out there that should be used. But you can imagine that there is some extension of something that looks like Python that could be the language there is. So we proposed a language called HACspec, which is a subset of Python. The cryptographers liked it, but nobody else did. Then we defined a new version of HACspec, which is a subset of Rust. Now the coders liked it, but the cryptographers don't like it anymore. So I don't know. It's not an easy. It's a social question. So it's not super easy to see.
And then, what do you propose OpenSSL itself do? Should it be rewritten? Should it be abandoned? I mean, I don't know. Like, it's C, right? C is. I work with C a lot. I hate it. I mean, I'm good, or I think I'm reasonably productive in C, but it's a terrible language. What do we do?
So, okay, OpenSSL, of course, is multiple libraries, right? So there is a crypto library, and the protocol library. The crypto library, well, on mainstream laptops and whatever, hardly ever uses the C code path, even though the C code path exists. Right? Usually it goes via the assembly port paths for a lot of crypto. So that's a different kettle of fish. But let's stay with the C world. There's definitely almost always a reference implementation in C. And since nobody really cares about it, nobody really uses it, it kind of stays that way for a very long time. And stability is good. So it's possible to imagine a subset of C, which is enough to write a lot of these crypto things, because it's just math, after all, with small loops, you know, where it is safe to write this language, and you can have tools that keep checking that it's actually doing the right thing. And there are tools that will do this for you. Right now, OpenSSL is not written in this style because there's too many callbacks, there's too much pointer manipulation and so on, that most of these tools just reject almost any algorithm in OpenSSL, except for the smallest functions that are doing just very simple big num stuff. Almost everything else, because of their levels of indirection, is out of scope for any tool. The protocol code, though, is using everything, right? Or the whole feature set of C. And that's well out of scope for any analysis, I would say. And there, I don't know what the right answer is. I have no...
So one thing that exists is something called fill-C, fill-C. That gets you some amount of memory safety. It has sort of a concurrent GC and other things in it. And I think I've convinced the author to add a FFI so you can use the assembly-coded crypto in OpenSSL. Anyways, thanks.